Now learning physics will be great fun with a physics teacher, a solution to all problems in physics.
The physics teacher.
Suppose you drop a block of mass m vertically onto a fixed ramp with angle theta with coefficient of static and kinetic friction mu. The block is dropped in such a way that it does not rotate after colliding with the ramp. Throughout this problem, assume the time of collision is negligible. Suppose the block's speed just before it hits the ramp is v and the block slides down the ramp immediately after impact. What is the speed of the block right after the collision? Clear? Now this question belongs to the concept of collision. And in such type of collisions between rigid bodies, here we have to deal with the effects of impulses. Clear? So this is a case of collision and we have to look for the effects of impulses. Now when I say impulses, the number of impulses acting here are the impulse due to normal force, so it is the normal force impulse. Clear? So I am denoting it here with letter IN. Clear? So this is the impulse corresponding to normal force. There is another impulse that is due to the gravity impulse, or the impulse corresponding to the force of gravity. So I am denoting this with IG. And there is one more impulse, that is frictional impulse. Clear? The impulse arising because of the force of friction, and I am denoting it here by IF. Now in this problem he is saying that we have to assume the time of collision to be negligible. So when the time of collision is negligible, so the effect of gravity is negligible here, so we are not considering this gravitational impulse. So the type of impulses we are considering here are the normal impulse and the frictional impulse. Clear? Now one more important thing which you have to remember while dealing such kind of problems, that in such situation the coefficient of friction is equal to the frictional impulse modulus divided by the normal impulse modulus. So we are using this formula here and these two impulses. Clear? Now in order to understand this problem in a better way, let's sketch the problem first. So here we have a ramp, this is the horizontal, this is the ramp, and let this inclination is theta. Now a block is dropped. Clear? Let its mass is m, and just before the collision with the ramp it has a speed v. Clear? Now the direction of velocity is in this direction of the arrow, and its component in this direction means along the ramp will be mv sine theta. I am writing in terms of momentum here, and in this direction it is mv cos theta. Clear? So I have resolved v in two rectangular components, one along the plane and another perpendicular to the plane or the normal to the plane, and correspondingly I have written the momentum components by multiplying these velocity components with mass. Clear? Now assume that after collision the block is assumed to be moving along the plane with speed say u. Clear? Which we have to find out here, and it is not rebounding in this direction. It is not rebounding in this direction means normal to the plane. Clear? So its initial momentum normal to the plane was mv cos theta, and its final momentum normal to the plane is 0. Clear? And the two impulses which we are considering here is this normal impulse, this is normal impulse, and another one is the frictional impulse. Clear? So if I write the normal impulse situation, so normal impulse is the final momentum along this direction, that is 0 because it is not rebounding in this direction and it is moving along the plane. So 0 minus mv cos theta. So from here I can write this, the magnitude of the normal impulse, as mv cos theta. Clear? Now what about this frictional impulse? So this frictional impulse is in the direction opposite to the direction of change in momentum along this plane. So the frictional impulse is in the direction opposite to the change in momentum. So this frictional impulse is IF and the change in momentum is mu minus mv sine of theta. Clear? Now from this result of IF I can write mv sine theta minus IF, and this is equal to mu. Clear? Now we have to substitute this value of IF, and that we can substitute using this formula. This IF, the value of IF is equal to mu times the magnitude of this IN. So from here we can write mu is equal to mv sine theta minus IF is mu times IN, and that is mv cos of theta. Clear? And from here we can write u equal to v sine theta minus mu cos of theta. So this is the desired expression. So just after the collision the block will move with this much speed along the inclined plane. Now in the next part he is asking that what is the minimum mu such that the speed of the block right after the collision is 0. So he is basically saying that what is the value of mu, or what value of mu should be chosen that this value of u becomes 0. So if we put value of u equal to 0, so we get 0 is equal to v sine theta minus mu cos theta, as v cannot be 0. So from here we can write that mu is equal to tan theta. Clear? So this should be the value of mu for this given inclination theta, so that right after collision the block will come to rest. Now in part B he is asking that suppose you drop a sphere of mass m, radius r, and moment of inertia beta times mr square vertically onto the same fixed ramp such that it reaches the ramp with speed v. Now suppose the sphere immediately begins to roll without slipping. What is the new speed of the sphere in this case? So we are going to sketch this situation first. So this is the ramp with inclination theta, and just before collision it has momentum mv sine theta in this direction, as v is in this direction. So this is the situation before collision. Clear? And just after collision, what this sphere is doing, it starts rolling along this inclined plane, and let the final momentum in this direction is mu. But here the frictional impulse is acting in this direction. This is the frictional impulse, and this frictional impulse will provide it rotation. Clear? And the inclination is theta, same. So as we have done earlier, like this equation, we are writing mv sine theta minus if, and that is equal to mu. Clear? Now here the frictional impulse is responsible for the rotation of this sphere, so the angular momentum about its center of mass can be written as the angular momentum about the center of mass can be written as frictional impulse into r, where r is the radius of the sphere. Now also he is saying that it starts rolling, so from here we can write that u is equal to r omega, where omega is the angular speed. Now we also know that the angular momentum is equal to moment of inertia times the angular speed. Now the moment of inertia here, it is given beta m r square into omega. Now using this result, you can write this L to be equal to beta m r u. So we have two expressions for this angular momentum. This is the second expression, and this was our first expression for the angular momentum. So using these two results, we can write IF r equal to beta m r u. So from here we get this frictional impulse equal to beta m u. Clear? Now using this result of the frictional impulse in this equation here, we get mv sine theta minus beta mu is equal to mu, and solving this we get u equal to v sine theta divided by 1 plus beta. So this is our desired result for the speed just after collision. Now in second part, again he is asking that what is the minimum coefficient of friction such that the sphere rolls without slipping immediately after the collision. So what should be the minimum coefficient of friction? So for this we need mu, and this mu is equal to IF divided by IN. Now again here the normal impulse is equal to mv cos theta, and the frictional impulse here is beta mu, and we have calculated u. So from here we can write this as beta mv sine theta divided by 1 plus beta. Now if we use both these results here, so I can write mu equal to beta tangent theta divided by 1 plus beta. So this is our desired result, and this is the minimum value of mu for which the sphere starts rolling just after the collision.